The objective of this lecture is to provide two examples demonstrating the application of the transport theorem to problems in kinematics. The first example is the following problem. A collar slides on a circular annulus. The annulus is configured as follows. It rotates about the vertical. So let's draw this picture. And it rotates relative to the ground. So the ground is labeled as shown, and the annulus rotates about the vertical as I indicated. The collar is located at a point P, as shown in the diagram, and the center of the annulus is point O. Now, the radius of the annulus is R, and the location of the collar relative to the annulus is described by this angle theta. The angle theta is the angle between a point at the top of the annulus, which I'm going to label Q, and P. So it's the angle from OQ to OP. Now, given that the annulus rotates about the vertical and the collar slides on the annulus, the objective is to determine the velocity and acceleration of point P, which is the collar, as viewed by an observer fixed to the ground. Now, in order to make this problem just a little bit more tractable, we're going to assume that the magnitude of omega, which is equal to omega, is equal to a constant, so that we don't have to deal with the rates of change of omega in the problem. Now, you can see that there are two rotations in this problem. So we have two rotations. So two rotations implies that we need three reference frames. Now, those three reference frames are as follows. The base reference frame is the ground, which I'm going to denote as G. The first rotating reference frame is the annulus, which I'm going to denote as A, and then the second rotating reference frame is the plane. Now we're going to be a little careful here. It's going to be the plane formed by the direction normal to the plane of the annulus and the direction OP. So that actually was a little bit subtle and maybe a little hard to see, but if you look at the direction normal to the annulus and the direction OP, you'll see that that forms a plane, and that plane rotates relative to the annulus. We'll get into describing this another way right now when we go through the frames. So we have three frames. We have the ground, which is the base reference frame. And then we have A, which is equal to the annulus. And then B, which is this plane that I just described. Now, what is that plane? Let's go back and look at this picture again. You can see that the normal to the annulus is actually along the direction OQ crossed with OP. So this is actually going to be the OQ crossed with OP plane. That's the plane I just described above. So now what we're going to do is we're going to fix coordinate systems in each of these frames. The origin of all these coordinate systems is going to be at O, because O is common to all three frames and it's fixed in the ground. I'm going to put UR along OP. UZ is going to be along OQ crossed with OP, and then U theta is going to equal UZ crossed with UR. The coordinates that are fixed to the annulus, EX is going to be along OQ, then EZ is going to be the same as UZ, and then EY is going to equal EZ crossed with EX. And then finally, the coordinates that are fixed in the ground, EX, EY, EZ is going to equal little ex, little ey, and little ez when t equals 0. Now let's draw a picture to see what this looks like. I'm going to draw this picture over here. Actually, let's draw the picture here. So EX is this direction that's along omega, which is also up. UR is the direction along OP, and then U sub theta is the direction orthogonal to that, and UZ is the direction into the page in this diagram, which also is equal to EZ. And because we're actually going to need it a little bit later, I'm going to draw the direction negative U theta. Negative U theta is given here. So this angle here is theta, and then that's the only, there's also an angle between the direction EY and U theta, which maybe I can draw just for completeness. This is the direction EY, and then this is the angle theta, and then this is UZ, and this is EZ. Now, once we have that, we can start doing the calculations. The position of P relative to O is equal to R times UR. Now, because UR, U theta, UZ is fixed in frame B, we're going to need to apply the transport theorem from B to G. So as a result, the velocity of point P is viewed by an observer fixed to the ground, which is equal to the rate of change in the ground of the position of P relative to O, is going to equal the rate of change in B of the position of P relative to O, plus the angular velocity of B in G crossed with the position of P relative to O. Now, because R is constant, the rate of change in B of the position of P relative to O is equal to 0. But in order to be able to do this calculation, I need the angular velocity of B and G. But we can see that the angular velocity of B and G is equal to the angular velocity of A and G plus the angular velocity of B and A, because first the annulus rotates relative to the ground, and then that frame B, which is defined by that plane which has its directions normal to the annulus and along OP, that frame rotates relative to the annulus. So that's the cumulative angular velocity. The angular velocity of A and G is equal to omega, which is equal to omega EX. The angular velocity of B in A is equal to theta dot times uz. So therefore, the angular velocity of b in g is equal to omega ex plus theta dot times uz. But you can see that that expression is not in terms of the coordinates that are fixed in frame B. So over here, we need to actually put everything in terms of the coordinates fixed in frame B. And you can see that from the diagram that Ex is actually equal to cosine of theta times UR minus the sine of theta times U theta, because Ex lies between UR and U theta, and the adjacent side is UR. So if I use that result over here, this gives me that the angular velocity of B in G is equal to omega cosine theta UR minus omega sine theta times U theta plus theta dot times UZ. So now, let's use that to be able to compute the second term in the transport theorem to be able to get the velocity as viewed by an observer fixed to the ground. This gives me omega cosine theta, it's omega bg, crossed with rp relative to O, is equal to omega cosine theta ur minus omega sine theta u sub theta plus theta dot uz crossed with r ur, which is equal to, well, u theta crossed with ur is minus uz, and uz crossed with ur is u theta. So this gives me r theta dot u theta plus r omega sine theta times u z. And I flipped the order after I took the cross products. That's how I got that. Now you can see that because the first term is 0, this gives that the velocity of point P as viewed by an observer fixed to the ground is just equal to the second term in the transport theorem, which is equal to r theta dot times u theta, and then plus r omega times the sine of theta times u z. So now we can actually differentiate that again to get the acceleration. So the acceleration of point P as viewed by an observer fixed to the ground is equal to the rate of change in the ground of the velocity of point P in the ground, which is equal to the rate of change in frame B of the velocity of P in G, plus the angular velocity of B in G crossed with the velocity of P in G. Now the rate of change in frame B of the velocity of P in G is equal to, since r is constant, I get r theta double dot u theta, and then I get plus, since omega is constant, I get r omega theta dot times the cosine of theta times u z. And then the angular velocity of B in G crossed with the velocity of P in G is equal to omega cosine theta ur minus omega sine theta u theta plus theta dot times uz crossed with r theta dot u theta plus r omega times the sine of theta times u z. So this equals, well, ur crossed with u theta is uz, so I get r omega theta dot cosine of theta times uz, and then ur crossed with uz gives me minus r omega squared cosine of theta times the sine of theta times u theta. And then u theta crossed with u theta is 0, u theta crossed with uz is equal to ur, so I get minus r omega squared sine squared theta times ur, and then uz crossed with u theta is minus r theta dot squared ur, and then uz crossed with uz is 0. So therefore, the acceleration as viewed by an observer fixed to the ground is equal to, well, let's gather all the terms. So if I gather the UR terms, I get minus R theta dot squared plus R omega squared sine squared theta times UR. And then the terms involving U theta give me plus R theta double dot, and then I've got minus R omega squared cosine of theta times the sine of theta times U sub theta, and then plus 2R omega theta dot times the cosine of theta times U z. And you can see that that last term, I've got R omega theta dot cosine theta, and I have another R omega theta dot cosine theta. So the acceleration now is given as viewed by an observer fixed to the ground. That's the acceleration of the collar as viewed by an observer fixed to the ground, expressed in coordinates fixed in the frame B, where B is that frame that I defined as the plane that's formed by the normal to the plane of the annulus, which is OQ cross OP, and the OP plane. That plane rotates relative to the annulus rotates relative to the ground, and this takes into account all of those rotations and gives me the acceleration of point P as viewed by an observer fixed to the ground. So that's the first example. The second example that we're going to study is what's called a spherical pendulum. So spherical pendulum is configured as follows. We have an arm which from which the end is, at the end of the arm is a point P. Now P is a length L away from the base of this pendulum, which is at point O, and O is fixed to the ground. And the position of the point P is actually known in terms of two angles. So these angles are actually going to be measured relative to a basis that is fixed to the ground itself. So I'm going to call this basis EX, and then EY, and then the downward direction I'm going to call it EZ. So here are the two angles. The first one is measured from this point, from EX to this line OQ, and it's called theta, where Q is the projection of P into the EX-EY plane. The second is an angle phi, and then the length of the arm, of course. I had it there before, but I put it back as L. Now the objective is to be able to use these two angles together with the length of the arm to determine the velocity and acceleration of point P as viewed by an observer fixed to the ground. So let's write the objective down again. The objective is to determine the velocity and acceleration of point P as viewed by an observer fixed to the ground. Now you'll notice that there are two rotations in this problem, just like there were in the previous problem, but unlike the previous problem where I had a physical object like that annulus, I don't have a physical object in this case to be able to describe these rotations. So we're going to need to do this a little bit differently. So we have two rotations, which implies, again, that we need three reference frames. Now let's think about how we're going to actually construct these reference frames. So let's draw this picture again so that we can actually look at these frames sort of one at a time in a new diagram. So here's the point P, and here's the point Q. Now, we have an angle theta, and we have another angle measured from EZ, which is phi. So the first rotation, you can actually see that there's the first rotating frame is actually this plane defined by the direction OQ and OZ. So OQ and EZ. So I'm going to call that the EZ OQ plane. And I'm going to shade it with a shading in red so you can see it. It's almost like a door that is opening up. That's kind of a good way to look at it. So there's the first rotation. So this is the EZ OQ plane, and it's equal to the first rotation. The second rotation is much more difficult to see, but we're gonna use a couple of other augmentations here to try to help visualize it. So if you see here, there's a direction that's normal to the EZ OQ plane, which I can actually form by taking the cross product of EZ with OQ. If I take the cross product of EZ with OQ, I get this direction. This is the direction EZ crossed with OQ. And I'm actually going to say along EZ crossed with OQ because it's a unit vector. That is actually orthogonal to both EZ and OQ. Now there's another plane that's formed in here, and it's formed by that direction, which is the direction along EZ crossed with OQ, and the direction OP, because the second rotation is by the angle phi. So there's a plane in here that actually is now defined. Now let me draw this picture in such a way that I can actually show you what that second plane is. So here is a parallel line to the original line OP, and then here is sort of the closure, which gives me this this plane. So I'm going to try to draw this in a way that sort of has a parallelogram kind of a feel to it. So there's the second plane, and I can actually shade that in blue. And you can see that that plane it rotates relative to the, it starts when phi is 0, so it starts sort of in a vertical configuration, and then it rotates by the angle phi. Now this is the plane which is formed by the direction EZ crossed with OQ and OP. And this is equal to the second rotation. So now we actually have a complete description of these different rotations in terms of planes. So now we can actually go ahead and we can start to set up the reference frames. So G is equal to the ground, and then A is equal to the EZ OQ plane, and then B is equal to, now remember what I called it. I called it the EZ cross OQ and the OP plane. So this is EZ crossed with OQ and OP plane. Now let's start fixing coordinates in each of these frames. I can do it from the last frame to the first, or vice versa. Let's start at the last frame. So the last frame is going to have one of its directions. I'm going to call that direction along OP. I'm going to call that direction UR. So UR is going to be along OP. Now I'm going to call the direction U sub theta is going to be along EZ crossed with OQ, because those are the two directions I used to define this plane. And then I'm going to call U sub phi equal to U theta crossed with UR. Now if you look, you'll actually see that now the basis is ordered UR, U phi, U theta, because if I take U theta crossed with UR, U theta is the third direction, and UR is the first direction, so 3 cross 1 gives me 2, which is U phi. So that's how I actually got this, because U theta is not the second direction, it's the third direction, so it's 3 cross 1. So that gives me, and actually I need to put an origin, so let's actually include the origin here before we move on to the previous, to the frame A. So origin is at O, UR is along OP, and then U theta is equal to along EZ crossed with OQ, and then U phi is equal to U theta crossed with UR, which again, I remind everyone, is equal to 3 crossed with 1. So now, let's look at the coordinates fixed in frame A. So this is the EZ-OQ plane. So what I'm going to do is I'm going to define a few directions here. I'm going to define ER to be along OQ. I'm going to define EZ to be equal to big EZ, where remember that big EZ was given. And then E theta is going to equal EZ crossed with ER, which also happens to equal U sub theta. They're actually the same direction. And the reason that they're the same direction is I define U theta as along EZ crossed with OQ, but OQ is the direction ER, so EZ crossed with ER is equal to U, is also equal to U theta. So E theta equals U theta. Now the last system of coordinates, the origins at O, and I already said that EX, EY, EZ were given, but we'll actually do it this way. EX, EY, EZ is given, but it also happens to equal ER, E theta, EZ when theta equals 0. So those, when these coordinates, when they collapse, when theta is equal to 0, we get that. Now we can actually draw a little picture here, which will be helpful in the diagrams. We actually need 2 pictures because we really need to figure out how A rotates relative to G and then how B rotates relative to A. So let's do the first picture. Let's look at how A rotates relative to G. So in that picture, I have these 2 directions, EX and then EY, and I have ER, and then I have E sub theta. And this angle is theta. And then EZ, the way this is drawn, is the same thing as big EZ, which is into the page. So I'm looking down on the pendulum from the top, if you want to call it that. The second diagram that I have is the one that relates B to A, and the coordinates fixed in B to the coordinates fixed in A. So if you actually look at that diagram, this direction here is ER, the direction downward is EZ, and then the direction which is defined by this rotation by this angle phi, that's UR, and then this is U sub phi, and then U theta is actually equal to E sub theta, which is out of the page because of the ordering of the basis, and then this angle is phi. Now we're going to actually start to work through the kinematics of this problem. So the important thing now is to start applying the transport theorem in the appropriate way given the parameterization of position. So we know that the position of P relative to O is equal to L times UR. And again, this tells us that we need to apply the transport theorem from B to G. So that tells us that the velocity of point P in G is equal to the rate of change in G of the position of P relative to O, which is equal to the rate of change in B of the position of P relative to O, plus the angular velocity of B in G crossed with the position of P relative to O. Now the first thing that we need to do here is we need to compute the rate of change in B of the position of P relative to O. But that's equal to 0 because L is constant and UR is fixed in B. So then we need the angular velocity of B in G. That's equal to the angular velocity of A in G plus the angular velocity of B in A. So let's do these. The angular velocity of A in G is equal to, well, let's go back and look at this diagram. We know that ER, E theta, EZ is fixed in A, and EX, EY, EZ is fixed in G. So you can see that the rotation by the angle theta in the direction EZ gives us the first angular velocity, which is, this is theta dot EZ. Then from the second diagram, I can get the angular velocity of B and A. So if I look at that diagram, we see that UR, U phi, U theta rotates relative to ER, E theta, EZ about the axis U theta, and the angle that describes the rotation is phi. So this is equal to phi dot times U sub theta, which leads to the angular velocity of B and G equals theta dot EZ plus phi dot times U sub theta. But the important thing we need to do here is we need to get this all in terms of coordinates fixed in frame B. So if we actually look at this diagram, from this we can actually see that EZ is equal to cosine of theta times UR, and then this direction is minus U sub phi. So I get cosine of theta, cosine of phi times UR minus the sine of phi times U phi. So let's write that down. EZ is equal to cosine of phi times UR minus the sine of phi times U sub phi. And again, that comes from the fact that EZ lies between UR and minus U phi, and the angle phi takes us to the adjacent side, which is UR. So that's why that's the cosine, the side that's multiplied by cosine. So as a result, I get that omega BG is equal to theta dot cosine of phi UR, and then minus theta dot times the sine of phi times U phi plus phi dot times U sub theta. And you'll see that that's already in the right order of the basis. So now we can actually use this result to compute the cross product. So when we compute the cross product, we get that omega BG crossed with the position of P relative to O is equal to theta dot cosine of phi times UR minus theta dot times the sine of phi times U phi plus phi dot times U sub theta crossed with L UR. So now we can actually go ahead and we can compute this cross product. So therefore, omega BG crossed with the position of P relative to O is equal to, well, if we look at this, we've got UR crossed with UR, U phi crossed with UR, and U theta crossed with UR. Well, we know that U theta crossed with UR is 3 crossed with 1, which gives us 2. U phi crossed with UR is 2 crossed with 1, which gives us minus 3. So what we're going to get is we're going to get L phi dot times U phi. And then we're going to get plus, we're going to get L theta dot sine phi times U sub theta, because U phi crossed with UR is U theta. So because the first term in the transport theorem to get velocity is 0, we obtain that the velocity of point P as viewed by an observer fixed to the ground is equal to L phi dot u sub phi plus L theta dot sine phi times u sub theta. So now we have the velocity. Now we're going to actually, the velocity is viewed by an observer fixed to the ground. So next, we're going to apply the transport theorem again to get the acceleration. So the acceleration of point P in G is equal to the rate of change in G of the velocity of P in G, which is equal to the rate of change in B of the velocity of P in G, plus the angular velocity of B in G crossed with the velocity of P in G. So let's actually compute the rate of change in frame B of the velocity of point P as viewed by an observer fixed to the ground. What do we get? Well, L is constant, so I get L phi double dot times u phi plus L times, I get theta double dot sine phi plus theta dot times phi dot times the cosine of phi times u sub theta. The second term is omega bg crossed with the velocity of P in G, which is equal to, well, if we go back and we get the angular velocity, we've got theta dot cosine phi ur, and then I got minus theta dot times the sine of phi u phi plus phi dot times u sub theta crossed with, I have L phi dot u sub phi plus L theta dot sine phi times u sub theta, which is equal to, so let's take this cross product and see what we get. So ur crossed with u phi is 1 crossed with 2, which gives me L theta dot phi dot times the cosine of phi times u sub theta, and then ur crossed with u theta gives me minus L theta dot squared cosine of phi times the sine of phi times u sub phi, and then u phi crossed with u phi is 0, u phi crossed with u theta gives me minus L theta dot squared times the sine squared of phi times ur, and then u theta crossed with u phi gives me minus L phi dot squared times ur, and then u theta crossed with u theta is 0. So when we start adding up terms, we get the following. Let's actually put the ur terms first. So therefore, the acceleration of point P is viewed by an observer fixed to the ground is equal to, so the ur terms give me minus, I've got L phi dot squared, and I've got plus L theta dot squared sine squared phi times ur. The next thing I have is I need the u phi terms because that's the second basis vector. So I get L phi double dot, and then I look for another u phi term. I get minus L theta dot squared cosine phi sine phi, cosine of phi times the sine of phi times u sub phi, and then plus, I have to get these last terms, the u theta terms, L theta double dot sine phi, and I've got L theta dot phi dot cosine phi, and I have another L theta dot phi dot cosine phi. So I get L theta double dot times the sine of phi plus 2L theta dot phi dot times the cosine of phi times u sub theta. And you can see that, again, in both cases, both the first example and the second example, we wrote the position in terms of coordinates, or we expressed the position in terms of coordinates that are fixed in the second rotating frame. and then we applied the transport theorem from that second rotating frame to the first frame, which is the base reference frame, which was the ground, to get both velocity and acceleration as viewed by an observer fixed to the ground. So the key takeaway from this lecture is that if you use the rotations in such a way that when you describe the position, you express it in coordinates fixed in the last rotating frame, you have to apply the transport theorem from the last frame to the first frame, which requires you to compute the cumulative angular velocity and then apply the transport theorem twice, once to get the velocity and then again to get the acceleration. And in the end, you're going to wind up with an expression in terms of the coordinates that are fixed in the second rotating frame, or the last rotating frame, which is exactly what we have in both of these examples. So as we move through other problems, we'll actually show how the transport theorem and other applications of the transport theorem work. But for right now, this is the end of this particular lecture, and we'll move on to other material in other lectures.